Response of an RC integrator to repetitive pulses. So we've taken a look at going from single pulses with a certain pulse width to a periodic set of pulses where we have a chain or a train of pulses. So now we're going to look at what are the characteristics then of the response of an RC integrator to those pulses. So let's assume that the capacitor in figure 2014 begins initially uncharged and determine the output voltage on a pulse by pulse basis. Okay, so there's 2014, there's our simple diagram. And so we can see a train of pulses here, 10 volt maximum, and then each one of them is numbered first, second, third, fourth, fifth. And we can see what's happening then with each iteration of one full cycle from negative to maximum to minimum, and then at the beginning of the next transition to maximum. So we can see here what's happening is we've got the circuit acting on that capacitor being charged not fully and then going into the next charging cycle. So we can see that what's happening here is during each discharge cycle going into the next charge cycle, we've got a little bit of voltage left over in the capacitor. So 2.3, 2.6, 2.68, 2.69, and so on, that stays within the capacitor as it holds its charge because it hasn't been given enough time to completely discharge. So if we look at the first pulse, during the first pulse, then the capacitor charges, the output voltage reaches 6.32 volts, 63.2% of that 10 volt maximum. Between the first and second pulses, then the capacitor discharges and the voltage decreases to 36.8% of the voltage at the beginning of the interval. So we can see here that relationship 3.68 times 6.32 gives us a value of 2.33 volts. So again, this goes back to what we've learned about the transient response and the levels of tau with each iteration. So now we're up to the second pulse, okay, going from negative to maximum, back to minimum, and getting set for the third pulse. The capacitor voltage then begins at that leftover voltage, 2.33 volts, and increases again 63.2% of the way to 10 volts. Okay, so now we're on this iteration. This calculation is as follows. The total charging range is 10 volts minus that 2.33, which gives us 7.67 volts. The capacitor voltage then will increase an additional 63.2% of the 7.67, which is now 4.85 volts. Thus, at the end of the second pulse, the output voltage is 2.33 plus 4.85, which gives us 7.18 volts. And we can see that at the peak then of the second iteration. Okay, now we look at what's going on between the second and the third pulse then as we're moving to the next low to high. So the capacitor discharges during this time, therefore the voltage decreases to 36.8% of the initial voltage by the end of the second pulse. So 3.368, okay, 36.8% times 7.18 gives us 2.64 volts at the in-between. Okay, so we're up just a little bit there. The third pulse then, at the start of the third pulse, then the capacitor voltage begins at 2.64. The capacitor charges 63.2% from the way from 2.64 to 10 volts. So again, we go through the same math, 63.2%, and then the difference in 10 volts and 2.64, which was right here at the beginning of the third pulse, gives us 4.65. Therefore, the voltage at the end of the third pulse is 2.64 plus that 4.65, which gives us 7.29. Okay, so you get the idea here. Between the third and the fourth pulse, the same thing. At the fourth pulse, the same thing. Between the fourth and fifth pulses, the same thing. And then what happens at the end of the fifth pulse. So what's happening here is iteration by iteration, the capacitor is not allowed to completely discharge, and therefore we see the pulse train rising and rising off of the floor here. So if a periodic pulse waveform then is applied to an RC integrator, the output wave shape then depends on the relationship of the circuit time constant and the frequency of the period of the input pulses. Okay, and we just saw that. So in this case, they're giving us a diagram here. Again, a 10 volt maximum, a period T. That period in this case is 10 times tau, the time constant. So the capacitor then in this case is fully charging and fully discharging in this example. When the pulse width and the time between the pulses is shorter than 5 time constants for a square wave, then the capacitor will not completely discharge or charge. And this is what we saw when we started this video. The input waveform that does not allow a full charge or discharge of the capacitor then, because we're at less than 5 time constants, 5 tau. An RC integrator then with a charging and discharging time constant equal to the pulse width of a 10 volt square wave input, then the output will gradually build up and then level off. So you can see here in this case we've got this set up so that we have a period equal to 2 time constants, or the period equal to 2 tau. If it takes approximately 5 time constants then for the output voltage to build up to a constant average value. Okay, again, this goes back to just exactly what we saw at the beginning of this video. Steady state time response. In the preceding discussion, the output voltage gradually built up and then began leveling off. It takes approximately 5 time constants for the output voltage to build up to a constant average value. This interval then is the transient time of the circuit. Once the output voltage reaches the average value of the input voltage, a steady state condition is reached that continues as long as the periodic input continues. This condition is illustrated then below in figure 2016 based on the values obtained in the preceding discussion. This is actually a very simplified way of looking at this. If anybody's a little more ambitious, you can look at this in an electrical engineering approach to this, where the calculus is used and differential equations will show you just exactly how all this really works. The transient time then for the example circuit is the time from the beginning of the first pulse to the end of the third pulse. The reason for this interval is that the capacitor voltage at the end of the third pulse then is 7.29, which is about 99% of the final voltage. So after approximately 5 time constants, then the circuit reaches its steady state condition. So you can see here then, they're saying after approximately 5 time constants, well, you can see here the floor is remaining constant, so we are in the steady state condition then as the pulses continue and the output then is displayed accordingly. The effect then of a variable resistor allows for a variable time constant. So instead of having a fixed resistor in here, if we put a variable resistor in here, we can now vary what's going on with the circuit and allows for a variable time constant. As the time constant then becomes extremely long compared to the pulse width, the output voltage approaches a constant DC value. So you can see what's happening here then. This value is the average value of the input. For a square wave, it's 1/2 of the amplitude. So you can see it's flattening out and flattening out as we continue. The effect then of longer time constants on the output of an RC integrator then tau 3 greater than tau 2 greater than tau 1. Hopefully you'll be working with circuits like this in the lab, and you can see it firsthand as you make the adjustments in your lab assignments. So the response then of an RC integrator to repetitive pulses. So let's take the effect on an increase of the time constant. So we've got a circuit here. We're going to determine the output voltage waveform for the first 2 pulses applied to the RC integrator. Assume that the capacitor is initially uncharged and the rheostat now is set to 5K ohms. So we determine our time constant, 50 microseconds. The first charging pulse then we can calculate using the exponential relationship that we've seen. And so we have 5 volts times 1 minus, this becomes t to the tau, so minus 10 microseconds over 50 microseconds, which gives us then the voltage then of 906 millivolts across the capacitor. Between the first and second pulse then, where we have discharging, we switch to the other relationship. Again, go back to your DC time constants, refamiliarize yourself with this relationship. This one and the previous one are fundamental to the charging and discharging using the exponential. So T over RC minus T over RC then gives us a value of 15 microseconds over 50 microseconds. We take the exponential of that, multiply it by that 906, and we get 671 millivolts. So the second charging pulse then, we end up with a final value problem. Actually, this is called a boundary value problem. Boundaries are final and initial in our math here. Again, this was a third exponential form that you should be familiar with from your DC course. So now in this case, 5 volts is the final value. The initial value was from the previous step here, 671 millivolts. We subtract that from the 5 value, take the exponential T over tau or T over RC minus 10 microseconds over 50, and we get then the capacitor value of 1.45. So if we graph this out, you can see what's going on here as we did our calculations over here. 906, 6.7. So there's 906, 6.7 during the charge and discharge phase, and then what goes on between the second and third pulses. So that is the RC integrator. Now we switch to the RC differentiator, and again we start with the single pulse.